Hi, this is Haishao Wang, and today we are going to talk about the path with minimum effort. And given the grade of the height, we can move from the top left cell to the bottom right cells, and we should return the minimum effort. The effort is the maximum absolute difference in the height between the two consecutive cells of the root. And for example, there are several routes that start from this cell to this cell. The one is like that, which is the optimal one. The maximum difference between the two consecutive cells is 2, which is 3 minus 1, um, and 5 minus 3, which is as 2. So we should just return the 2. And for the root like 1, 2, 2, 2, 5, the maximum difference is 3 because the 5 minus 2 is equal to 3. And um, for the first idea come to in my mind is just traditional breadth search problems, but we cannot solve it by using that because this is a little bit tricky. In the traditional breadth search problems, and for example, there's a node and just return this to node. And for example, we start from this node, and then we just go its neighbors, and then we go its neighbors. And actually, the edge weight is all equal to 1. So we make sure that every time we find its neighbors, it must be the most close um, node that is from the starting node in the current situations. However, for this case, it might happens like this case. The address for A to B is 1 and B to C is 2 and A to C is 100. And if we start from the A and we go through its neighbors and we just update the distance from A to B to 1 and A to C is 100. Then we go from the B and we found that the distance from A to C is greater than the distance of the A to B plus distance of B to C. So we should update the distance of C by 1 plus 2, which is 3. So every time we'll just pop up the most uh, the minimum effort that for this cell, and then we'll just um use go through its neighbors. And that's the basic ideas of these problems. Let's just code it out. This gets the shape of the height, and this is initialize the effort for each cells. And the visitor should also be a matrix to denote whether that cells is already get the optimal values or not. And we should um, initialize the top left effort to be 0, and it should be, and I prefer to use dx and uy to denote the movement of the directions. So here we saw our loop. Um, we just check whether we already pop it from the heap in the previous process. If yes, we should just continue because we already make sure that it has the optimal values. We should not take it into considerations. Else we just return true and we'll just start for x1 is equal to check whether the xy is in the boundaries of the height. We calculate the new effort between these two nodes, and the effort is calculated by ABS of height. And we get the max effort as is that. And if the max is less than the effort of xy, which means that we should update the effort for xy because we'll find the optimal values for that. Yeah, we should also append to our heap. And we just return the effort for n-1, n-1, which is like this point. And let's check. Oh, yeah. Oh, yeah, it seems works. What happened? Oh, I think it's a problem like that. Yeah, because I record this is yeah now it's at 1 a.m. and my brain is didn't work. And it works. Yeah, thanks for watching. Good night.